ruin
No,
the.
exactly.
I don't want to ruin the
Yeah,
aftertaste.
perfect taste.
But I will ruin the aftertaste with something that's too fast. So, what's the intuition? So before, right, you had some notion of continuous maps for maps from where to where. You had some notion of continuity for maps F from R to R. Do you agree?
Yep.
Okay. And so let's actually just write down this definition. So F from R to R, okay, I'm going to write very small. F from R to R is continuous if what? For any epsilon, right? Greater than 0, there exists a delta such that.
Or it doesn't have to be greater than 0.
Oh yeah, greater than 0, whatever. Wow, you failed to earn a mark for that. That's crazy.
I would have got 100 if I put delta to 0.
Okay, epsilon around 0, delta zeros, and I guess for every point A, for every point A, in the domain, whatever it is, such that f of a ball of size delta around point A fits into a ball of size epsilon around f of A. Okay. So ball of size, ball of size, I don't know, whatever, ball of size delta around any point x, I define as the set of points y, such that the distance between x and y is less than delta.
Less than 0. Yeah.
Okay, it's less than 0. Okay, integrate. So right now we just defined continuity for R. Okay. In fact, if I do nothing, I literally keep this the same, except for now this distance is the usual Euclidean distance. I've now defined continuity from Rn into Rm. We're done. In principle, if this is all you wanted to do, you could stop here and be happy. However, let's introduce the notion of a topological space. And what is the idea, right, behind this? Continuity, what does continuity say, right? For every epsilon, I have a delta. Okay? So it's kind of saying that, if I have some points that are close here, if I have some points that are close in here, then they must be coming from something that was close in the domain. If I have some points that are near each other in the range, they must have come by mapping of f from points that were close together in the domain here. Okay? And I want to point out that this is not the same as points are close to here implies points are close to here. It's not the same. Okay? And okay, we'll think about why a bit later. But the claim about continuity is that points that are close in the target must have come from points that were close to each other in the domain. Okay? So perhaps the natural thing about continuity isn't necessarily like the points themselves, but kind of which points are close to each other. Do you agree? So the main idea of topology is kind of, instead of talking about individual points, like think about groups of points that are in some sense close. Think about which points are close in some sense. In some sense. And so we need to, and so to specify kind of which points are close and which points aren't close. Like If I tell you, okay, these points are close to each other, what kind of object is that?
A ball.
Not necessarily a ball, but a
Solid.
simpler words. If I have a bunch of points, that is a
Group or sets.
set. That's a set. That's not a group.
Yeah,
Group is
sorry.
addition. But that's true. So I need to tell you which points are close. So I need to give you a bunch of subsets in some sense. Okay? This is like a loose thing. This doesn't immediately give you the definition. And now I will fail to recall the definition of a topology, and that will be very funny. And this will have a number of suggested exercises. So, definition. The pair x comma t, x comma tau, where x, where x is a set, and tau is some subset of the power set of x. So it's like, it's a bunch of subsets of x. It's some collection of subsets of x. Okay. It's called a topological space.
So then tau is also like a set of sets, right?
Tau is a set of subsets of x.
Yeah.
And x is a set.
Yeah.
Is called a topological space. If, and I think there's 3 conditions. Okay, first condition.
When you're in topology.
Yes, that's why I'm trying to
Yeah,
remember.
first condition. Okay, let's do the easy one. X and the empty set have to be in the topology. Yeah, so tau is called the topology on X. So X and tau is the topological space. Tau is the topology because tau is, I'm going to tell you which sets of points are like close in some sense. Okay. X and empty set are the sets in tau. Then what do I want? I want an arbitrary union to be also in tau, and we're going to see why this is the intuitively makes sense as the definition. So if I have some, so if u sub alpha for some indexing set set lambda, let's call it lambda, for some indexing set lambda, if u sub alpha is in the topology, where alpha is just some indices, not necessarily countable. That's why I'm using some other arbitrary set to be the indices, because this could be uncountable, whatever. Then that implies that a union of all of these sets, u alpha is also right? This is like a union of a bunch of subsets, so it itself is a subset. And so the claim is that if I have a bunch of subsets which are in the topology, then their union is also in the topology. And then the third thing is that if I have u1 up to un, so some not.
Sorry. I mean, you shift
Yeah,
the computer
sure.
a little bit, please.
Okay, this is better. If I have some u1 up to un, some finite number of open sets, then the intersection of finitely many such sets is also in the topology. Okay? Do you kind of agree with this?
Yeah.
Okay. What is why does this kind of make sense? Sorry, and I forgot to say one last thing. And an element of the topology, so u and tau, these we call open sets. Okay. So this is what we call a topological space. The topological space is essentially, I have some space, and then I have to tell you what are the open subsets on this space. Do you agree? Okay. And so, in principle, for the same space, I could give multiple different topologies on it, and so tell you like different points are close. like different sets of points are close. And then what you could then say is, in principle, you could have like different continuous functions on the same domain. But don't worry about this. What is yes?
Is the set of just x and that always like the simplest?
Yes,
Yeah.
that's true. I could just have a topology where it's just
X.
all the points are close, or like have a set that has no points and that's considered close. And then in that case, and that's like the most rigid topology. But then this topology will never really tell you much about your like it will tell you very little about your functions. Oh, it's not entirely useless, but it doesn't tell you much. Okay, so why is this kind of the roughly why is this the right thing? What is the understanding of open sets we have from R? We have like open intervals, right? And those are called open. And so you know that, okay, if I have like infinitely many open intervals and I take their union, then clearly I still get something that looks, kind of like something like an open interval. Do you agree? And then I know that if I have, finitely many open intervals and I take their intersection, then the intersection is still some open interval. Do you agree? Why do I not want to take an infinite intersection of open intervals? What could happen if I take an infinite intersection of open intervals? What could that be?
You keep going like this.
Yes.
And then you shrink down to like
A single point.
And
Yes.
then it's like
I
close.
could have something that's like minus 1 over n, 1 over n, and then I could have like an infinite, an infinitely shrinking open interval. The only thing that's in the intersection of all of them is 0, and clearly a single point shouldn't
really
quite be open set. So in our usual definition, so this is probably the right definition. Okay, so this is probably the right definition to make. We have this definition now. Okay, very good.
So the bottom one, that's why it has to be finite, right?
Yeah.
That's why the finite intersection, infinite union.
Okay.
Okay, and to remember that, you can think of open intervals. If I have like infinitely many open balls, is that still kind of the same vibes as an open ball? Yes, maybe they're disjoint, but still same vibes. But then if I have finite intersection, is that still like an open ball? Yeah, kind of. So good enough. Okay, so now why did I want to do this? I wanted to define continuity. The definition of, right, so there's actually two things we want to do. First thing is, I set out to define continuity. I want to define continuity. Second thing, I want to check that this new definition of continuity is the same as this old definition of continuity. Do you agree? And so these are two steps. So I'm going to define continuity, and then I'm going to give an exercise. Because, okay, to check if this definition of continuity on Rn is the same, what do I need to tell you about Rn? I need to make it into a
Topological space.
I need to make it into a topological space. So, Archit, what do I need to specify on Rn to make it into a topological space? I need to tell you,
What's that?
Like
yes, I need to tell you tau, which
Yeah,
subsets are
topology.
open. Okay, so I need to give you a topology on Rn, and then I need to give you a definition of continuity, and then you have to check if that continuity under that topology is the same as this one. Okay, and that will be the exercise. So I give you two things. Okay, I'll restrict myself to one word. So definition, we're almost done. So a function, so let x, y be topological spaces. A topological space is a pair, like I need x in the topology, but writing a second letter is too hard. Just say x, y are topological spaces, and people know, okay, there's some topology on it. Some like set tau. Okay. Let x, y be topological spaces. We say, and f, a function from x to y, a map from x to y. We say f is continuous if for any open set V in Y, so if I take an open set here, that implies that the preimage of V is open in X. So roughly, another way of writing it in terms of like these taus, yes,
What's open in X?
is an open set in
Okay.
X. Sorry. So what does this mean? In terms of like these letters, in terms of these letters, I could write U in the topology of Y implies F inverse. Well, I was using V. Sorry. V in the topology of Y implies F inverse of V is in the topology of X. Okay. If points, and once again, if points are close in the target, they must have been close in the domain. This is not the same as the other way around. That's an open map, and that's not the same. Okay, good. And so now I need to give you a topology on Rn. Okay, and so this is the exercise. I extend this further. Okay, I extend this further by saying what? What did I want to say? Sorry, yes. So, let, let, suppose X, my set is Rn, okay? Then I define the topology in the following way. The topology is then all sets U, all subsets U of Rn, such that for any point in the set, there exists a little ball around the point that's fully contained in U. Okay. So what does this mean? I have my Rn, okay? And suppose I have some set in Rn. This set is going to be open under this definition if and only if I take a random point in here, I can draw a little circle around it that still fits inside of the whole set. Okay?
Fits completely, right? Like
Fits
the entire ball is inside of the space.
Yes. As
It's
written.
open, so you won't have it like.
Well, no, I'm telling you what it means to be open.
Yeah.
It is open if there exists a ball that I can fit inside of this. And so now, the thing you now have to prove is show that, if this is our definition of continuity, the preimage of an open set is an open set, and this is my topology on Rn, prove that this definition is equivalent to this definition with this topology, and vice, so you want to prove one direction and the other direction.
Yeah.
This is the suggested exercise for the week. Maybe we'll come up with a suggested exercise for the implicit function thing. Maybe I'll just give you a bunch of derivatives and you're going to compute a bunch of derivatives. Actually, I can just open Moncrief and say compute all of these derivatives. Very good. Okay, this is it for the bonus section.